Hi everyone, welcome to the conference again. Before the talk, I'd like to make two short announcements. First, after this talk, please turn on your video. We have a group video, group photo, whatever it is. You have a group photo, you should have your picture there. And also at 12 o'clock Toronto time, your third talk, we'll have a Steve Kulla's birthday celebration. Because we're on the Zoom, so bring your own food, your own drink then. Okay, so let's start the talk with young Bruinier. He will talk about 7 value of the high automorphic green functions. Please, Yang.
Thank you very much, Tonghai, for the introduction, and thank you very much to all of the organizers for putting together this great conference to celebrate Steve's birthday. I wanted to begin by mentioning that I first met Steve in a somewhat indirect way, namely by meeting some of his doctoral students, some of his PhD students. So in, I think it was in 1999, I met Jens Funke at the Max Planck Institute in Bonn. So there was a workshop, I think related to Borchards products or something like that. And that was certainly very nice. And just a year later, I think I met Tonghai when I was as a postdoc in Madison. And certainly with both of them, I had very fruitful collaborations over all the past years. So that was very nice. And also, I think like 1 year later, I then really met Steve in person. I think that was at a workshop at the Schrödinger Institute in Vienna at that time. That was shortly after I met Tonghai. And yeah, I must say, it was great to meet him. And certainly, I've really learned a lot from him and his inspiring mathematics through his papers and also somehow the collaboration on joint projects. So certainly, thank you, Steve, for all of that. Today, I wanted to talk about work with Tonghai Yang, I just mentioned, and Stefan Ehlen, namely on these CM values of higher automorphic green functions. Yeah, so let me start right away. So now it works. So maybe I have to remember how to click forward and backward. So this is forward. So let me first begin by recalling what the classical automorphic green function is. So the classical automorphic green function is a function that lives on the modular curve x. So x is defined as usual as the complex upper half plane modulo the group SL2Z. And more precisely, this automorphic green function lives on the product of x with itself. It's a function on x cross x. It depends on additional spectral parameter s. And I want to assume first that real part is bigger than 1. And then you can define it as an infinite sum. So basically, you take here some kernel function that depends on this point pair invariance. So you have z1 minus z2, absolute value squared over 2 times imaginary part of z1 and then imaginary part of z2. And then you average this, and you take this as the argument of the Q Legendre function. And then you average over the group in order to get an invariant function, so really a SL2Z invariant function. Because here in this integral kernel, we have some point pair invariant. It's actually invariant in both variables and defines a function on x cross x. And this is the so-called automorphic green functions for SL2Z, or sometimes called resolvent kernel, because it is actually the resolvent kernel for the hyperbolic Laplacian. So it's a very classical function that plays an important role in the spectral theory of automorphic forms. You can now characterize this function by certain properties. So let's look at that. We already mentioned that it is SL2Z invariant in both variables. And it is a smooth function outside the diagonal. On the diagonal, it has a logarithmic singularity. So as Z1 goes to Z2, it blows up with the logarithm, and then you also have to wait by the order of the stabilizer of the point Z2 ESL to C. Okay, so it has this logarithmic singularity along the diagonal, and then there are further properties. So first of all, it is an eigenfunction of the hyperbolic Laplacian in the first variable. So if you take for I1, so then you have the hyperbolic Laplacian somehow in the Z1 variable, and it is an eigenfunction with eigenvalue s times 1 minus s, and then the same you also have in the second variable. And then also you can somehow control the growth as imaginary part of Z1, say, goes to infinity. So you have some moderate growth, or actually some decay. So this is also something you can easily check. And then there is a little proposition you can prove, that is, these properties here characterize this automorphic green function uniquely. So if you like, you can forget about the definition using the Legendre function and just take that there is this function, and then it's characterized by these properties that we wrote down. Okay, and so I want to somehow look at certain special values of the spectral parameter S and special values of the arguments. For the spectral parameters, we'll look at positive integral values, and for the arguments here on the modular curve, we'll look at CM points in particular. For the spectral parameter in particular, if you look at S equal to 1, then you see that this green function is harmonic, basically, up to the problem that it doesn't converge at S equal to 1. But you can show that there is a continuation, and so you can make sense of the value at S equal to 1. And there you see that you get something harmonic. And somehow you get a harmonic function on x cross x. And harmonic functions are not so far away from holomorphic functions, and therefore not so far away from algebraic or arithmetic geometry. So it's not so surprising that at spectral parameter S equal to 1, this may be particularly interesting. But then also, so this is something that Gross and Zagier noticed, at positive integral spectral parameter, you see some interesting properties. Okay, so let's look a bit at these properties. So we want to look at CM points. So recall that the point in the upper half plane is called a CM point if it lies in some imaginary quadratic field. So it's the solution of a quadratic equation, az squared plus bz plus c. And we have the discriminant here of this quadratic form, b squared minus 4ac, which should be negative in order for this quadratic equation to actually have a 0 in the upper half plane. And then also we want this to be positive definite. So this is the condition here that a should be positive. So we can look at these CM points, and then D will be called the discriminant somehow of the underlying quadratic form ABC here we have here. And then, as we all know, the group SL to Z acts on these on the set of these CM points of fixed discriminant with finitely many orbits, and we can push it down to the modular curve x, and we get a special divisor on this modular curve. So this is the divisor given by CM elliptic curve whose ring of endomorphisms contains the order of discriminant D in their endomorphism ring. For this divisor, we count points with multiplicity given by the order of the stabilizer. Okay, and now we want to look at values of these green functions at CM points. And in order to have more flexibility, turns out to allow some additional twisting by Hecke operators. So we can slightly modify our green function GS. So this is called here GS upper n by hitting this function with the nth Hecke operator. So then we get this GSM. And so this function here now has, as you can easily see, a logarithmic singularity along the nth Hecke correspondence. So nth Hecke correspondence defines a divisor on x cross x, and this GS upper m has a logarithmic singularity now along the nth Hecke correspondence, which you can view as a special divisor on x cross x. Okay, and now Gross and Zagier noticed that certain linear combinations of these twisted green functions here are particularly interesting. And the linear combinations you have to take are as follows. So you fix a positive integer k, and then you take a weakly holomorphic modular form of negative weight. So here this M shriek, I'm using Don Zagier's notation, stands for the weakly holomorphic Moyer forms of weight 2 minus 2k for SL2Z. It has some Fourier expansion. So for instance, if the weight is 0, then you could take the classical J invariant. And I want to denote the coefficients by CF of n. And somehow the existence of this weakly holomorphic Moyer form is by Serre-duality equivalent to the fact that if you take this linear combination, or maybe here I should take this linear combination, so you take the coefficients with negative index and then take Hecke operators on the space of cusp forms of weight 2k, that this is identically 0. So you can somehow view this weakly holomorphic form here we have here as determining a relation among in the Hecke algebra on cusp forms of dual weight 2k. So this, but it's quite useful to write this down in terms of this weakly holomorphic forms. So anyway, if you have such a weakly holomorphic form, you can look at the Fourier coefficients and write down a linear combination of these GKM. So now here we specialize for the spectral parameter the positive integer k, and we take this linear combination involving the Fourier coefficients of f. Okay, and now we can look at the CM values of this green function, and there's an important conjecture of Gross and Zagier regarding the CM values here. So if we take 2 CM points in the upper half plane of discriminants D1 and D2, and I want that the pair of CM points Z1, Z2 is not contained in the divisor of this GKF, so this linear combination of green functions, then I can look at the value of this linear combination of green functions at these CM points. And the conjecture is that this is not some random number, but it's really given by the logarithm of some algebraic number, alpha, which is contained in the class field, so in the compositum of the ring class fields of discriminant D1 and D2. And moreover, there should be a compatible Galois action. So somehow the Galois group here of this class field acts then on the alpha, and it also acts on the CM points, and these actions should be compatible. Okay, so this is a somewhat striking conjecture, because this gk, if k is not equal to 1 or 0, but some large positive integer, then this is far away from being algebraic. I mean, this is just an eigenfunction of the Laplacian with integral eigenvalue. So there's really no reason a priori to assume that these Cn values are algebraic or given by logarithms of algebraic numbers. Okay, so why should we then believe in this conjecture? Well, there are a couple of heuristics and results that you can observe, or that have been proved. So for instance, first you could look at the case where k is equal to 1. 1 is certainly a positive integer, and this was the place where the green function is harmonic. So where you would expect that it could be related to some algebraic object. And in fact, it turns out that if you define the regularized value of this green function for s equal to 1 in the right way, then it's basically given by the logarithm of the absolute value of the difference of the two j invariants. So j of z1 minus j of z2 is a rational function on x cross x. You take its absolute value squared, and then the green function is just a logarithm of that. And there you clearly also see the logarithmic singularity very nicely. And in this case now, this conjecture is a theorem which simply follows from the theory of complex multiplication, because we know. Yep. Was there a question? No? Okay. Because we know that the values of the j function at Cm points, they are in these ring class fields and have a compatible Galois action. So by complex multiplication, we get somehow the conjecture in this very special case. But then also Gross-Cohn and Zagier carried out numerical computations to give evidence for the conjecture, and also they proved some average results. So where they averaged over all Cm points of discriminant D1 and all Cm points of discriminant D2. And they did that for odd positive k, and showed that what you get in this way is the logarithm of a rational number, which is what you would expect by the conjecture. So this is in accordance. And then later, over the years, there have been proved a couple of more results that support the conjecture. So by Shu Zhang and Anton Melit, Marina Wiazowska, Ying-Kun Lee, in particular, there are some results when the Cm fields agree. So when the underlying imaginary quadratic fields here agree, so discriminant D1 differs from the discriminant of D2 just by a square, and then some further average results and things like that. Okay, so now I want to explain a little bit what Stefan Ehlen and Tonga Yang and I proved here regarding this conjecture. So we proved somehow a partial average result. So we only average over Cm points of one discriminant, and for the other Cm point, we allow arbitrary Cm points, so the individual points. So let's look at the result. So we take a positive integer, and again, our negative weight weakly holomorphic form that somehow determines the relation in the Hecke algebra. And we take two negative discriminants. We assume that D1 is fundamental, and somehow the underlying imaginary quadratic fields should be different here for this result. And then we take any Cm point D2 of discriminant D2. And then we can look at the quantity. We take this green function, somehow averaged according to the principal part of f. And in the first variable, we average over all CM points of discriminant D1. In the second variable, we allow individual points. And then we could show that this partial average is really logarithm of an algebraic number in the right class field. So exactly, essentially the ring class field of discriminant D2. And we had to somehow allow a certain denominator here, which is independent of F and somehow most of the other things. And also, we have a compatible Bauer action here.
Well, I have a small question.
Yeah, sure.
Jan, so in this result, you have the absolute value of the algebraic number alpha. Is this absolute value a serious restriction? I mean,
I think so. Yeah. So this really naturally comes up. So maybe one can do some, but that one would have to do some, have to find some additional ideas to get rid of this. So I mean, you're already in the k equal to 1 case. You see that where we get the logarithm of the absolute value of this difference of the j's. So it's really we get the absolute value there. So it's not so easy to get.
But are there any proposals even for a formula conjecturally where one gets rid of this absolute value?
That's a good question. I don't know. Yeah, but certainly interesting question.
I mean, I think the analogous situation in the Kronecker limit formula is that you get in Kronecker limit, you get log of absolute value of the eta function. And there's no way that in the literature that I know, and this is a very, very fundamental theory. So if there were such a thing, it would be extremely famous where you could get log eta instead of log absolute eta in Kronecker limit. So, I mean, that's an analogous and even more famous and ancient question. So,
and the same thing comes up in Stark's conjecture as well.
Exactly.
Yeah. So that's right. So that's the same type of problems.
Real anyway? All these green functions are real valued anyway, right? So they have to be logos of absolute values of stuff.
That's also true. So somehow, I guess, nevertheless, you could ask whether you can come up with some. I mean, somehow this should be related to some relations in some Chow groups. So in principle, they should be given by some rational functions. And so you could ask about actually the values of these functions. And there should be some relationship. But it's true. I mean, these green functions, by construction a priori, they are real valued, and therefore, at the outset, only see the absolute value. Okay. Further questions at this point? Or maybe I move on. So that now there are a couple of things one can notice, or I would like to remark. So in particular here you see, so this is a stupid observation. If D1 has class number 1, then certainly there is just 1 point here, so there is no real averaging. So then this would give the conjecture in this case, or we get the conjecture in this case. Actually, you can do a little bit better by allowing somehow twisting by some genus characters, and then you actually get the conjecture whenever the class group has exponent 2. So this is what we get out of this result. And then also, I'd like to stress that very recently, there's a new preprint by Yinkun Lee on the archive, who was able to remove this partial average. So by introducing new ideas and extending this approach by these new ideas, and in this way, under some very mild restrictions, he is able to get the full conjecture. So somehow this is an advertisement to look at his paper on the archive. Just came out like 10 days ago. So I think it's very, very nice result. Okay, so after this advertisement, so let's move on and see how we approach these results. So Our approach is to actually look at a more general setting, look more generally at automorphic green functions on orthogonal Shimura varieties. And one can also define higher automorphic green functions. So one can look at special values of the spectral parameters in this more general setting for orthogonal Shimura varieties. And we can prove a result for these green functions. So there's a more general result that can be specialized to the case of modular curves. So in this way, we also obtain some higher dimensional analogs. And here somehow, maybe I want to mention some key ingredients. So theta, as in the title of the conference, is very important. So somehow the regularized theta correspondence due to Borchards, also some work that I did, certainly somehow the idea or the concept of seesaw dual pairs that was invented by Steve is very important for these results. Also some differential operators and results of Duke Lee and Ehlen on harmonic mass forms of weight 1. All right, so let's look at the more general setting. We look at Shimura varieties, orthogonal Shimura varieties. Setting is we take a quadratic space over Q of signature n, 2, and then we can look at the G spin group of this quadratic space, which is a central extension of the special orthogonal group of V. And there's a corresponding Hermitian symmetric space. So somehow generalization of the upper half plane. There are different realizations here. I'd like to work with a realization as the Grassmannian of -2 planes. So we take subspaces in V tensor R. These subspaces should have dimension 2, and the condition is that the restriction of the quadratic form to the subspace should be negative. And also we put an orientation on that. That way this D has 2 connected components. And then we take a compact open subgroup of the finite adels and look at the usual double quotient. We have the Hermitian space cross H of AF. On the right, we mod out the compact open. On the left, we mod out the rational points of the G spin group. And this then gives a quasi-projective variety of dimension n, which generalizes modular curves in the special case where n is 1, and modular surfaces, say Hilbert-Moyer surfaces, when n is 2. And these special cases will be important to recover this Gross-Zagier conjecture. So this will be, the results on the Gross-Zagier conjecture will be obtained by specializing n either to 1 or to 2. Okay, so now what are these automorphic green functions in this case? So maybe we have to fix the data a bit more precisely. So we want to take an even lattice in our rational quadratic space. So the quadratic forms would have integral values. And we want to take our compact open such that it stabilizes L hat, the completion of the lattice, and acts trivially on the discriminant group. Okay, so this should just be sufficiently small. And then for every mu in this discriminant group, this L prime is the dual lattice of L modulo L. So this is some finite abelian group with a quadratic form, called the discriminant group sometimes. So for mu in this L prime mod L, and a positive m in this coset of the integers, we can define a special divisor ZMU on the orthogonal Shimura variety. So this ZMU generalizes the Hecke correspondences that we had on x cross x. And now we can define the automorphic green function. So this is maybe a somewhat lengthy formula. So this generalizes this sum involving the Q Legendre function. So the automorphic green function on the Shimura variety for this special divisor is defined as a sum over lattice vectors here. So you sum over the coset defined by mu, and you want the quadratic form to be equal to m. And then there's some special function. Maybe it's not so important what this is in detail. So f is the Gauss, classical Gauss hypergeometric function. And then it depends on the spectral parameter s. And what is interesting is that it really depends on the projection of our lattice vector lambda to the orthogonal complement of the two-plane defined by z. Or, I mean, you could also write it slightly differently and say it depends on the projection of lambda to the two-plane z. So this is what it really depends on. And then green functions of this type have first been considered by Oda and Suzuki, and I constructed them in a different way, and they turn out to be quite useful also in the theory of Borcher's products. So they converge whenever the real part of S is bigger than S naught, and this S naught, n over 4 plus 1/2, is the harmonic point. So this is also an eigenfunction of the Laplacian, and it has a logarithmic singularity along this special divisor ZMU, and that way it's a bit similar as the automorphic green function for SL to Z we saw before. So let's make this more precise. If we take for our lattice the lattice of 2 by 2 matrices of so this is 2 by 2 matrices, and the quadratic form is the determinant, and this has signature 2, 2, and one can show that the Hermitian space in this case can be identified with H cross H, and this green function for the special divisor ZM mu, well, mu is, since this is unimodular, this mu information, there is just a trivial coset, so we can drop this. So the phi m is really this Hecke translate of the classical resolving kernel we saw at the beginning. And then also you can look at lattice of signature 1, 2, which you obtain by taking the trace zero matrices. So you take a sublattice in this M2Z. This has signature 1, 2. And also there, so in this case, then the Hermitian space is just the upper half plane. So you get a function that lives on the modular curve x, no x cross x. But you can show that the phi m in this case is just the classical automorphic green function with a Q Legendre and so on, with shifted spectral parameter. And for the first argument, you plug in the special divisor Zm. And then the second argument is somehow the variable. So these are two identities. And actually, the second identity is the one we use to prove the theorem I mentioned. All right, so what can we say about special values of the spectral parameter of this automorphic green function? The spectral parameter S basically gives us the eigenvalue under the Laplace-Beltrami operator on the orthogonal Chabot variety. And we want to look at somehow S naught, so this is this n over 4 plus 1/2, is the harmonic point. So there, this function has the right to be related to algebraic or arithmetic geometry, so to say. And then, as in the case of the Gros-Sage conjecture, we want to shift the spectral parameter by positive integers. So we want to look at S naught plus J. Okay, and then it turns out that if we look at this, we can look at the special shifted parameter and also take weighted green functions. So here we take, as before, a weakly holomorphic form. Now the weight kappa minus 2j. So this has to be adapted to the dimension of our Chabot variety. So kappa is 1 minus n over 2. And then we can look at weight kappa minus 2j. And then little technical thing, this would be vector valued forms, taking values in some finite dimensional ray representation. Okay, but just weakly holomorphic Moyer forms. If you like, you can ignore the vector valuedness, then just think of things as the J function, but in smaller weight. And then this has some Fourier coefficients, and we can use this, again, take the pole at infinity and weight these automorphic green functions at spectral parameter S0 plus J. Okay, so this is the analog of what we did in the Gross-Zagier conjecture. And then there's a proposition that says that these weighted guys can be obtained by lifting harmonic mass forms. Namely, or maybe if here we stick to the, let's stick to the weakly holomorphic forms first and come to the harmonic mass forms later. So somehow this, for this weakly holomorphic form F, this weighted higher green function phi j of z, h, f, so this guy up here, can be written as a regularized theta lift. Namely, we take our weakly holomorphic form, hit it by the raising operator, the mass raising operator that takes the weight up by 2, hit it j times with the raising, so that brings then the weight to kappa. Kappa is 1 minus n½ So this is exactly the negative of the weight of the Siegel theta function. So we can pair this with the Siegel theta function for the lattice L. Then this has weight 0, and we can integrate over fundamental domain. And then since the F has singularities, the integral has to be regularized in Borchardt style somehow. And then you can make sense of that. And it turns out this weighted linear combination of these higher green functions is just this regularized theta integral. Okay, so that's good, because this gives us the possibility to use some theta techniques to study the CM values. So how do we get CM points in this setting? So let me recall that. I want to look at small CM points. They are given by a two-dimensional negative subspace of V that is defined over Q. So V has signature n,2. So this is a maximal negative definite subspace defined over Q. And then we can tensor this subspace with R. Then we get a real two-plane, which defines then a point in the Hermitian space. So that was the Grassmannian of negative two planes. And then we can have the choice of the orientation. So we actually get 2 points in D. And also we can look at the special orthogonal group of U, or at this extension at the G spin group. And this then comes with a map into the G spin of the big quadratic space. So actually this G spin U will be K cross for an imaginary quadratic field. And so defines this torus in the G spin of V. And then at the level of Chaumont varieties, we get a 0-dimensional sub-Chaumont variety, which is a CM cycle. So the ZU, so this is a 0-dimensional Chaumont variety sitting in our orthogonal Chaumont variety. And also our negative space U defines lattices. Namely, we can take our original lattice, intersect with U. This gives a negative lattice, negative definite lattice of dimension 2. And we can do the same with the orthogonal complement and get a positive definite lattice of rank n. And we have corresponding theta functions, theta n, which has weight -1. So this is the theta function for this negative definite two-dimensional lattice, so to say this binary quadratic form, and then p, theta p, the theta function of this positive definite lattice, which then has weight n/2. Okay, and now we can go a step further. We have this theta function for the negative definite two-dimensional lattice. This has weight -1. And we can fix a pre-image under the mass lowering operator, so something in weight 1. And to be able to find a pre-image, we have to go away from automorphic forms with moderate growth. We have to look at harmonic mass forms. So there's always a harmonic mass form. I want to denote by G and H. with a property that if I hit it with a lowering operator, I get this binary theta function. And then this has a holomorphic part, as usual, denoted by the plus here. And then we can use this guy to give a formula for the CM value of the higher green function at the CM point ZU, comma H. So H is in the finite adults of this torus. So somehow this allows to move in the class group among the classes of these binary lattices of discriminant equal to the discriminant of A. Okay, so if we want to look at the CM value here of the higher green function, then it is given by the constant term. So this is the CT of some Q series. So if you like, a formal Laurent series. And how does this work? Well, the F is a weakly automorphic Moyer form, so this clearly determines a Q series. Then the theta p is the theta function of this positive definite lattice. We can look at the Fourier expansion, get a Q series. And then here this Gn plus is the holomorphic part of this harmonic mass form. So this gives us, again, a Q series. And so this only has finitely many negative coefficients. This also, the theta p only has non-negative coefficients. So we can take here now the Rankin-Cohen bracket. So there's a bilinear operator that takes modular forms cross modular forms to modular forms again, but you can also just consider it on Q series if you like. So this guy, if J is 0, then this just reduces to multiplication. Now for higher J, it's a little bit more complicated. It's a bilinear expression involving derivatives up to order J. So this Rankin-Cohen bracket is again a Q series. We can multiply these Q series, get a new Q series, and then we want to take the constant term. So, and this gives the formula for the CM value. In particular, here we see if F has integral coefficients, certainly the theta function has integral coefficients, then the CM value is an integral linear combination, explicit, of the coefficients of this Gn plus. In that way, we get some explicit formula. Of course, now we have the problem that we have to understand the coefficients of these Gn pluses. And there's a nice theorem about these coefficients that generalizes previous work of Stefan Ehlen and Bill Duke, Jinkun Lee, that says that the Fourier coefficients here of these harmonic mass forms, they are given by logarithms of algebraic numbers in the ring class field of discriminant D given by the discriminant of the binary lattice. So there's a little denominator we have to put here, but at least this is independent of N and H. A little thing we lose, but in principle, we have a very nice formula for the Fourier coefficients here. They're given by logarithms of absolute values of quantities in the ring class field. And now this is very good. So also I should mention that these quantities are really something you can compute. So there's an algorithm to compute these guys. So Stefan Ehlen wrote quite impressive programs to actually compute these guys. And also I mentioned that there were successor results by Duke Lee and Ehlen in a little less generality that were of this type. Okay, so we have these quantities, and now as a corollary, we can combine this with a formula we had before. The CM value of the higher green function is given by the constant term of this F times the Rankin-Cohen bracket. And now if F has integral Fourier coefficients, we get an integral linear combination of the coefficients of this Gn plus. And we know those are given by logarithm of algebraic numbers in this ring class. Therefore, we see that these CM values are of this type. And also we get a compatible Galois action. So the Galois action then comes by somehow varying these h's, which are in the finite adults of this torus. And now we can somehow identify the points of the zero-dimensional Shumo variety with a class group using class field theory, and then we have compatible Gauer actions here. Okay. Now we can apply this in the special case of interest to us, but maybe before I want to do that, I want to think a bit more about these quantities. Maybe there's also some more structural understanding we could try to get. Some sense they are nicely given by this algebraic data, but why is this so? Can we say maybe a little bit more about it? Somehow we can say something by averaging over the CM cycle Z of U. And this is very much motivated by work of Jared Schofer, another former PhD student of Steve, and Steve himself. What we can try to do is somehow motivated by the work of Schofer, average over these points ZU, H. So they are all single points in this CM cycle Z of U. And we can just take the average. So sum up all the values and see what we get. And then if you think of the formula, we had here the individual values, they are given somehow by pairing the F with this stuff here. And there the H dependence is only in this lowering pre-image of the binary theta function. So on the right-hand side, we have to average over these harmonic mass forms, these G and H. And the point here is if you average over these guys, then you get the central derivative of the incoherent Eisenstein series of weight 1 for the binary lattice N. So in some sense, you can view these G and H's as substitutes for this incoherent Eisenstein series when you don't take the average, but look at the individual points. And this incoherent Eisenstein series of weight 1, so this was studied in many papers of Steve's, in particular in the IMRN paper that he and Michael Rappaport and Tonga Yang wrote, I think, which they call the tiny paper, and which gives an interpretation of the coefficients of this incoherent Eisenstein series derivative in terms of arithmetic degrees of special cycles on the moduli stack of CM elliptic curves.
I make one comment about where tiny came from. So
yeah, that's very good.
Yeah. So at some point, we were developing all these ideas and these theories and higher dimensions and so on and so forth. And Dick Gross, so we're always looking at ON2 and N is 1, it's a modular curve, and N is 2, it's blah, blah, blah. N is bigger and bigger. And Dick made the trenchant comment. He said, well, what happened to N equals 0? And so we said, well, N equals 0, what could be there? And so that's just a tiny example. But it turned out that we learned so much by studying this example. And so I should thank Dick for his trenchant comment that what about N equals 0? So that's why it's tiny. So anyway.
Yeah, thanks. So I think this is really very important basic case here. And somehow much of the structure that you see for higher N actually can be reduced to the case where N is equal to 0. So say you have some pullbacks and arguments like that. So this is a very important case, I guess. Yeah, so and somehow this paper in some sense tells us that these harmonic mass forms here, the Gn, I mean, this will be replaced by these derivatives of the incoherent Eisenstein series, and we should get to a formula then involving the incoherent Eisenstein series. And here the coefficients are even more explicit than for these harmonic mass forms. So there it's really something you can compute, involving doing some local Whittaker function computations. So this is even more explicit. So now let's look at the average formula. So now here I want to replace the single values by the average over the cycle. Then I weight by the degree of the cycle. And I haven't changed much compared to the previous slide. I did change something. Instead of taking a weakly holomorphic Moyer form, I took a harmonic mass form here of weight kappa, which is 1 minus n over 2 minus 2j. And then the CM value for this harmonic mass form for these higher green functions weighted now by this harmonic mass form is, again, you get the constant term of this Q series here, now dictated by this incoherent Eisenstein series. And in addition, you get a second term, which is the derivative of a Rankine type L function. So here I denoted this L of G, U, S. So this is a convolution L function of a cusp form G of weight 1 plus n over 2 plus 2j. So this is the dual weight for this kappa minus 2j. So you get the cusp form here of this weight and the theta series, theta p of weight n over 2. So this is somehow the quantity you get here. You get the central derivative of this convolution L function appearing. And now we observe if f is weakly holomorphic, as we had it before, then this psi operator here of the weakly holomorphic form is 0. So this guy is 0. So the second term is not there. And we only have this constant term as we had before. Also, if j is 0, so somehow then the green functions are just the usual green functions at the harmonic point, then somehow a formula of this type was used in a little bit older work of Tonga and mine to somehow get another approach to the Gauss-Sagier formula. And this now looks very much like a higher weight analog. And somehow it suggests that this first quantity should have so first of all, this quantity, the full right-hand side should have an interpretation as some Archimedean contribution to some height or intersection pairing. And here this constant term quantity, or the negative of it, should have an interpretation probably as some non-Archimedean intersection pairing. Of some cycles, they should be defined on some variety fibered over the orthogonal Schmor variety. So say you take the Cougar-Satake abelian scheme and maybe take some fiber powers and then try to construct some special cycles that are fibered over these special divisors, CMU or the CM cycle, as was done in the case of modular curves by Berlinski and Shu Zhang and studied there. So it would be very interesting to get a better understanding and see if one can do something with cycles in somehow varieties fibered over these orthogonal Schmor varieties and understand that in this way. Okay, but maybe at this point I shouldn't speculate too much. So now I want to get back to the Gauss-Sagier conjecture and somehow see how we can now use the general results to prove it. Okay, I already mentioned that we obtain this by specializing to the case where we take a very special lattice of signature 1, 2, namely the 2 by 2 matrices of trace 0 with a quadratic form given by the determinant. In this case, this point S0, this harmonic point, is n over 4 plus 1/2, with n is 1. So we get 3 over 4. And now this higher green function, say you evaluate it at the harmonic mass form whose pole is of the form q to the negative m. So I denoted this by fm. You can do that. And then this higher green function is by this identity relating the orthogonal automorphic green function to the classical resolvent kernel. In this case, you get by what you get is this higher green function is really the classical resolvent kernel function at spectral parameter 1 plus 2j. And then in the first variable, you average over the CM divisor or special divisor of discriminant m. And then the second variable you have as a variable. So in particular, this means these gk we obtain for k odd. I should say that you can also do something for k even. There you have to modify the theta function, the Siegel theta function, by plugging in some extra degree 1 polynomial, and then you get something similar, a similar identity, and then you get something about the gk for all positive k. And so somehow this variant of the theta function is related to the, if you think of the Shimura correspondence, or already if you think of unary theta functions, there you have the weight 1/2 and the weight 3/2, and this is somehow similar. Yeah. Okay, so you can do that, and then somehow maybe little problem here is here we're having signature 1, 2, and then this weight kappa that I had, this was always 1 minus n over 2, so this is 1/2 here. So somehow these forms we plug in would be half integral weight, but in the Gauss-Zagier conjecture, it was integral weight forms. And there's a certain lifting that relates these two weights. So the so-called Zagier lift from weakly holomorphic forms of weight 2 minus 2k to forms of weight 3/2 minus k. And for every discriminant d1, there is a lifting like that. So it's like if you realize Shimura correspondence using theta correspondence, you have these different theta liftings here. And now the theorem you get by specializing our general result is that if we have an F weakly holomorphic form with integral coefficients, then we can evaluate the higher green function spectral parameter k at the CM divisor of discriminant d1, and for the second argument we can plug in a CM point of discriminant d2, and then this is equal to the constant term now of the Zagier lift of f times this Rankine-Cohen bracket involving this harmonic mass form of weight 1. Okay. And in particular, now using in addition these results on the coefficients of this Gn plus I showed you, and somehow on the Galois action, we get that this quantity is really of the form logarithm of an algebraic number in the class field, the ring class field of discriminant D2, where we have to allow somehow this little denominator R. So this is the formula we really get. And here we can move back to the theorem we had at the beginning and see that this really gives this result in this case. All right. Yeah, maybe this shows how to reduce this result to this more general case. And I also have some numerical examples, but maybe since time is more or less up, maybe they are not so interesting right now. And, maybe I want to skip this for now and move to the last slide. And thank you all for your attention. and wish you happy birthday, Steve, again. Thank you.
Okay, thanks. Yeah. Good talk. Any questions or comments?
These ranking type products that you're talking about, these are between half integral weights, right? I mean, the ranking product between half integral weights that you're, I mean, it's a theta function, and the other one was half integral weight, I think that.
You mean these L functions, or
Yes, you said
this ranking
derivatives
convolutions integral? So maybe let's go back to where these were. So I think that was here, right? Yeah, it depends on n, right?
Yes.
If n is odd, so like the case we would have for the modular curve that I took for the example to somehow get this result on the Gross-Zaghi conjecture. So there n was 1, and then this would be half integral weight, and in this case the theta p. So p would be a positive definite one-dimensional lattice. So then it would be really a convolution of a half integral weight form and a unary theta series. And you can also reduce that in this case then to the Hecke L function of the Schmor lift of the half integral weight form. Actually derivative at the center then, or you can do it for the L function itself. So there's this relationship, but then for higher n, it can also be different. So for instance, if n is equal to 2, then here you would have forms of integral weight and a convolution with a binary theta function associated to a so you have a lattice of rank 2 then, and a binary theta function of weight 1, and then you would take this ranking convolution. And then if you go up, you have this, somehow it depends on the parity, so to say, of the n, whether you have half integral weight or integral weight for these convolutions.
Are there any generalization of these things to higher groups? I mean, this is just basically GL2, and I mean,
I think I mean, L functions of this type, these convolutions. So I think there's a paper by Piatetsky Shapiro.
Those are there. I meant your other. I mean, the thing about this green function, which is pretty much something which is devoted to upper half plane, and that's.
Well, yeah, the green function. I mean, in general, there's this notion of resolvent kernel.
Yes.
Well, here the green function is really, in the general situation, it's on the orthogonal Schmor variety, which is higher dimensional. So the dimension is n. So if you look at higher dimension, certainly here it's green functions on these n-dimensional Schmor varieties. But also you could look at other groups and try to see what you can do here, what you can do there. So somehow since here the techniques are related to the theta correspondence, I mean, if you wanted to obtain results of this type, you would have to look at the situation where you have some dual reductive pair. But for instance, you could look at the pair of SPM and ON2. And actually, Steve and Jens and I have looked at that quite a bit, and gets much more complicated. But it's very interesting. So there are, whenever you have these dual reductive pairs, you can try to play these tricks. But I mean, the notion of resolvent kernel and so on is really something you can look at for the Laplace-Beltrami operator on any Schmor variety.
Thank you.
You're welcome.
Other questions?
Hi, Jan, beautiful talk. May I ask a quick question about the same theorem?
About hello, about
Hello.
which
Hello,
one?
yeah.
Same theorem or
Yeah.
some? Ah,
This one, sorry if I missed something, but if you're in the setting where the dimensions are correct, so that the Rankin-Selberg function is central, the central derivative value, is there any way to use this result to show that that is a period in the sense of Kontsiewicz and Zagier when you have this? I mean, it's something they don't really describe very well, but somehow they can get from their formula or from the way that you do prove it, this assertion that the central derivative value is a period. You've also got that here.
It's a good question, and I guess I haven't thought about it, but maybe complicated. So.
But in principle, it should be doable. Yeah?
Okay, so this is always a bit difficult with statements like in principle it's doable. Maybe. So I really don't have a very good feeling. In some sense, the integral is, I mean, the integrals we have are so I don't know. So I would have to look at it. Or one has to look at it. So it's not so clear. I mean, these integrals and period identities and so on sometimes are very tricky, and I'm a bit careful.
Okay. Yeah. Okay. Now that I'm asked one naive question, I ask one more. Do you make any conjectures for the setting where the imaginary quadratic field is replaced by a real quadratic field? Or when you replace,
so this is also a very good question.
You replace behavior points with these geodesic cycles. I mean, in principle, or morally, or whatever, many of the calculations carry through. Do you think about this or make any conjectures, at least, if you haven't proved anything? I mean, if I imagine you can prove.
And so we haven't looked at that. I mean, if you. So maybe there could be some interesting relationships with the work of Henri Darmon and Jan Bonk, for instance.
I should. I mean,
so that would be. I mean, they are in some sense doing this theory of singular moduli and these things with these co-cycles, and have some very interesting results in this direction. And it may be possible to also have, so to say, higher weight analogs.
I mean, this
higher weight, or maybe they already have. Maybe Henri should comment on that.
Yes.
If there's hope to, maybe then somehow your cohomology theory has to involve some coefficient system in addition. Certainly, that would be very interesting. I don't know, Henri, do you have any idea?
We thought about this higher weight thing a little bit, but there's a difficulty. We don't have any interesting result. I mean, I don't want to know why, but it's a little bit technical. But somehow one can't make sense really, in an obvious way at least, of the values of higher weight. I mean, I have a student who's developing the theory, Isabelle Negrini, who's developing the theory of higher weight rigid meromorphic co-cycles.
Yes.
We can't make sense of their values.
Okay. But is this a rationality problem, or is it?
It's a well-definedness problem. I mean,
I see. Okay,
you don't know how to define associate a meaningful numerical invariant.
And you're using this.
There's some nice idea that allows you to do this, but we just haven't been able to do it.
Are you using this machinery with the Borchards? I'm sorry if this is maybe not the right time to ask, but are you using this setup with the regularized theta liftings and this work of Bruinier, Young, and various other collaborators? Are you using this setup?
Oh, definitely. The ideas that came up in Jan's lecture are very much present also.
I see. Okay. Sorry. Thank you, and thanks. And yeah, thanks for the talk.
Other questions, comments?
Yeah, I was wondering whether there is what is the local Archimedean theory corresponding to these constructions, if is one, if it can be isolated from the rest of the and representation theoretic, I mean.
That's also a good question. In some sense, these computations we're doing here are pretty global, and would be interesting to work out some local interpretations. And so somehow I think this would go more into the direction of Steve's idea of these arithmetic theta liftings, and where you can, I mean, so somehow there you have also these arithmetic Siege formulas and things like that, and there you have local and global, and so somehow it may be possible to understand this, what somehow local versions, say a local Archimedean or non-Archimedean version of this result is by looking at these local arithmetic theta functions and corresponding theta liftings, but somehow we haven't thought about it.
That says like the no crossing here on, and if the very special case modular curve, this is really like same cycle in the Kuga variety intersection that prime here, the final part.
You mean, I see. So you mean you're asking about somehow intersection theoretic description of this quantity.
Not really, no.
So
no,
this,
I was
this
actually.
could be, so somehow, so if you look at the case of the modular curve, then somehow quantities here, so this would be these CM values of the higher green function, and this should give the Archimedean height pairing of special cycles, so CM cycles in Kuga-Sato varieties over the modular curve. So you can have the modular curve and then take the universal elliptic curve, cross itself, and in there you have a cycle defined by the graph of complex multiplication. And then somehow if you take fiber powers over these CM elliptic curves, then you get cycles in these Kuga-Sato varieties. And so somehow here, at least in the case where n is equal to 1, the interpretation should be just the Archimedean height pairing of such cycles. So where you have a CM cycle, and then in the addition, another CM cycle that is somehow dictated by, so it's also a linear combination of CM cycles dictated by somehow the pole of f at infinity. So there's a particular linear combination. So
that answers a question I maybe should have asked, and but my actual question was whether there are representation theoretic techniques buried in some of the calculations, because I see, for example, the Rankine-Cohen bracket is a representation theoretic construction, and there were some others earlier on, but this I'm just trying to understand the global
that's
structure.
certainly very good and important question, and understanding that better. So we've somehow really looked at the global results here, and understanding that better might also have some importance for generalizing that. So somehow to the question that was asked earlier, but somehow in terms of representation theory, it's not so easy. I mean, for instance, one thing which is not so easy is to make sense of these harmonic mass forms or weakly holomorphic forms. So somehow the decay modules were described by Steve and Kathleen associated with these, but I think to really get a conceptual understanding, one really would have to do still quite a bit. And I don't know if it's really possible. But so somehow the feeling should be, it should be possible somehow. Maybe we're missing something.
I mean, one point in this whole, many of these calculations is that frequently, I mean, traditionally in the theory, when you pass from the classical automorphic form, a holomorphic cusp form, let's say, to the corresponding representation, you basically, you create this infinite dimensional space with all these other vectors in it besides the lowest weight vector, which is the holomorphic one. And then in some sense, you ignore all those other vectors, right? I mean, so, you know, now you have this infinite dimensional representation, and so you call it pi, and it's pi. And before you had f. But you see in these calculations that Jan is doing, frequently you can see that what happened is that the important vector for doing the analytic work was not the f or the corresponding lowest weight vector, but something deeper inside of the discrete series. So you see a number of points here where you see some raising that's done to make the weight match up with some other theta lift, but now you're no longer working at the holomorphic, the lowest weight vector in that representation, but still you can do something like that. So there were several places like that. So I think that's an interesting point, that the question is, you know, in these classical calculations, you almost never see the use of these other vectors, but the Rankin-Cohen is a particular example of that. Just a comment.
Okay, probably we should go take a group photo, and let's thank Jan again.
Thank you.
So stay here, we take a group photo before we